Good morning, everyone. Today, it's my privilege to talk about my research on sustainable Portland limestone cement-based ultra-high-performance concrete. Let me start by giving you a bit of the research context. Being sensible of climate change and natural disaster is, of course, very important, especially that last month we just experienced 2 major hurricanes, and that 40% of the global population actually lives near coastline. Data tell us that if disasters that caused more than 1 billion in damage are increasing rapidly, and hurricanes, storms, and flooding are by far the one that caused more damages. So the future will likely be worse than that if we don't take, of course, any action. Although we have different way to mitigate this natural disaster and defend like our coastline, in the past, coastal communities really relied on our structure, such as seawalls and breakwaters. And today we have over 20,000 kilometers already covering concrete. But this concrete is aging, often showing significant damage, and it was designed with just a pure engineering function, missing an important opportunity to benefit the surrounding ecosystem. For this reason, at the University of Miami, different research teams started to develop the Sea Hive project. Sea Hive project is an ongoing project of a hybrid coastline protection system. It's based on an 18-foot long hexagonal concrete tube, and its modular design and the perforation on the side allows the water to flow within the system, dissipating wave energy and protecting coastline against storm surges and coastal erosion. It's a concrete mixture, sustainable concrete mixture. It's offer benefit of, it's biocompatible with ecosystem, helping, for example, in restoring natural coral reef. So far, we have 3 pilot projects that have been already deployed in South Florida, and another one using a 3D printed concrete technology is currently under development. So in this presentation, we don't have time to talk extensively about the Sea Hive project, but we're going to focus on its materials. So we said that to have more durable concrete structure, we really need to step up with better materials. And traditional UHPC is a great option for that, but there's like 2 challenges with that. One is related to its materials that have a really high carbon footprint, and also those materials, especially steel fibers, are very expensive. And both of these conditions really prevent the use of traditional UHPC in a larger scale. So we said, okay, how can we address both of these challenges? So we tried to improve sustainability of UHPC formulations by replacing the traditional type 1 and 2 cements with PLC and adding low carbon SEMs such as ultrafine limestone, fly ash, and slag. We use a coarser sand, and we addressed also the cost issue, evaluating synthetic polyethylene fiber to replace at least partially the steel ones. What have we done exactly? So we use locally available materials. We developed 5 different formulations that differ from each other for the proportion in the bonder materials and also in the type of fibers that they use. The first one, we developed one that uses only steel fibers, one that is a hybrid system with both polyethylene and steel fibers, and the last 3 with only polyethylene fibers. We kept the water-to binder ratio constant at 0.2 and the addition of super plasticizer at 2% by volume. and we compare everything with commercial UHPC. So this is the first results of our ongoing research that I'm showing you. This is related to autogenous shrinkage, which you might know is like a real issue for UHPC because it can cause internal stresses and crack our concrete, so affecting the durability. In this case, our formulations actually suffer less autogenous shrinkage than the commercial UHPC. This was mainly due for the different SEMs that we use, and that they created like for all these formulation a microstructure that show larger pores, and that helped to decrease the capillary pressure that formed during hydration. Also, was interesting to notice that to see that Slag performed better than fly ash, and this was because of the sulfur dioxide content that was higher in the Slag, and then its chemical expansion helped to offset part and mitigate the effect of the shrinkage. Of course, we evaluated the compressive strength of these mixtures up to 91 days. And we saw clearly two effects among the formulation that we developed. One is due to the fibers, where steel fibers perform better than polyethylene ones. And this is it was proven even in the literature, where if you had up to 2% of steel fibers, you actually benefit strength. While for polyethylene fibers, there's more challenges when you mix them. They form kind of agglomeration, and these agglomeration, they created weaker spots that they led to a premature failure of the specimen. Also, we could see that the different SEMs help in the strength development. The limestone and with a feeder effect, and the Slag at early ages, while the fly ash contribute more at later ages. But you might have noticed that no, actually, one other thing. So at 91 days, also one of our mixture overperformed the commercial HPC and met the 120 megapascal strength requirement that most of the most used UHPC definition requires. You might have noticed that these strengths are not particularly that high for UHPC. That was the reason why we define our like a ultra high performance concrete, because as we said, we expected results not that high because of the high replacement level of SEMs and PLC that we use. And also because we didn't use any kind of high temperature curing condition, but just like normal curing condition. Also, when you test UHPC, usually standard refer to cylinders, and we got our results on cubes. Cylinders have the challenge that they require high load capacity machines that like not all the labs have available. So we said, okay, with what we have, let's see if we can run a comparison between cubes and cylinders. And actually we saw that when you test cubes are actually an acceptable alternative, because there was a nice correlation between the results of these two specimen geometries. And so they are an alternative when you don't have those high load capacity machine to test the strength of UHPC. The other comparison was actually because of the number of specimens that we had to test, we used plastic molds. And we compared them with steel molds. And you actually saw that like the more likely brittle behavior that you have with high strength concrete, when you use steel molds, you avoid even minimal geometric imperfection that in this case cause a loss of strength around 15 to 20%. And testing steel cubes with steel molds, we met the 120 megapascal value at 28 days instead of 91. We test also flexural strength with a classic 4-point flexural test. When you test fiber reinforced concrete, you really want to exploit, like get some toughness and have that kind of deflection hardening behavior. And that was the case for all of the mixture that we developed and the commercial HPC. We saw that mixture with steel fiber really showed a high fracture peak strength, while polyethylene fibers really help in providing a better first peak strain capacity. And that was the reason why the mixture that had both fibers really benefit from both of these effects. To evaluate the sustainability of our approach, we ran an analysis considering the global warming potential of these mixtures. In this case, we used as a reference different commercial UHPCs that had like an average of global warming potential that it was more than 1,000 kilograms of CO2 equivalent per cubic meter of concrete. As a comparison, if we consider normal strength concrete, we are approximately like a third of that value. But with our formulation, actually, we had an average of 640. That was meant like a reduction of 40% compared to commercial UHPC. And this was important to address the feasibility of our sustainable approach for these formulations. We ran also a series of other tests evaluating even fresh properties of these mixtures. We saw that, for example, like measuring the flow, the mixture with steel fibers was really showed a self-consolidating behavior, while it was more challenging with the polyethylene fiber, even if consolidation helped a lot in that. But you can find more details in the link on the slide. Also, this research is ongoing. We are currently evaluating durability, exposing these formulation concrete in seawater and also to hurricane condition. And more data will be hopefully presented at the next ACI. I thank you for your attention, and I acknowledge and thank you all the partners of this research, and I'm more than happy to take any question you might have.